All right, well, our problem today is taking a look at the chain rule, our favorite rule for differentiation, one and all, and seeing what it can tell us about anti-differentiation. Just to warm you up and remind you about what the chain rule is about, it's about taking derivatives of things like this. So if I'm trying to take the derivative of sine of x squared, then it's, I don't know, you might have memorized it as this the derivative of the outside times the derivative of the inside. So you take the derivative of the sine and you get cosine, and you leave the inside alone, times the derivative of the inside, which is x squared, and you take that derivative and it's 2x. Yes. Some crazy professor may have asked you to think about this in terms of this, and you probably ignored her, but you should not have, because we're going to be using this type of symbology here, where we're using the Leibniz notation and all. And I'll explain what all this means. And then, just to verify, if you ask Mathematica, of course, it can just pump it out. But we're talking about the theoretical underpinnings. We're not talking about the knowing how to do something as much as understanding why it works that way, so that we can do more advanced things and more advanced thinking. Okay? So get your mind out of, well, I just need to know how to do this, and I'll just stick it into Mathematica and I'm done, and that's everything, and that's my work. A lot of work goes on in here. Okay, or should be. So let's go on, all right? So we got the chain rule for differentiation. Here we've written it like Newton would write it, with lots of tick marks and stuff. And so the idea is that if we have a function that can be written as a composition of two functions, so here's my big function, and I can write it as the composition of two functions, then we get this chaining out. And the hardest part of this is asking ourselves, what does that mean? What does that mean? Right? You got f prime, but you got the g of x in there. What's the difference between that and this over here? Yeah, that's right. I knew that you had those questions. Maybe you don't, but I doubt it. Okay, well, when we used the definition of the derivative, we proved that rule as long as we can prove all the rules hold for, small conditions on the functions, such as these limits exist. And with this rule right here, if you write it out, what this means, this is implying that you're going to take the derivative of this thing with respect to this whole thing right here. So it's really df g of x, dg of x. So you're thinking of g of x as a block, as a variable. Now that's tough. That's tough. So you might just get rid of the indication that it's a function of x and maybe just put a single letter there. But that doesn't hide the fact that it's actually the name of an expression, so we'll traditionally use some other letter that has not been clouded in our minds about what it means. So, and that letter is usually u, so we'll write it like this, that the derivative of this whole expression here, this composition here with respect to x, can be chained as the derivative of f with respect to u, which is the next layer. How does it change with respect to what the next layer is, and multiply that times how does the next layer change with respect to the final layer, x. And with the understanding that this equality here only holds if after we are done, all the u's we find, we substitute back in g of x, so that we have an expression of x over here, and we have an expression with respect to x over here. Now, let's take this and ask ourselves, what about the antiderivative of both sides? Well, the antiderivative of both sides with respect to x, right? Those are going to be equal. That equal symbol still holds. That you take you take this thing that's equal to this thing, and you look at the family of functions whose derivative gives me this, then you're also looking at the family of functions whose derivative gives you this. Now, I want to pull these apart because I want to notice what the fundamental theorem of calculus says about these two things. Well, first of all, on this is the antiderivative of a derivative. As a matter of fact, for an indefinite integral, we write indefinite integrals as antiderivatives simply because the fundamental theorem of calculus is actually a statement about the definite integral, that antiderivatives come into play with finding areas directed areas between curves and the axis, if you remember all of that. So this is why we even use these symbols interchangeably with antiderivative. So what is this equal to? Well, we're just undoing the derivative. It's f of g of x plus any constant. And so we get a whole family of things whose derivative with respect to x will give me this back. Yeah, you can keep saying it to yourself, but it's obvious, right? Well, maybe nothing's obvious. But right here, I want to do something tricky. I want to do something tricky because this thing technically is an expression of u. And then right here, when we write that u, we mean this thing ought to end up being an expression of x. But what could we do here? Well, I want to ask you a question. What if this whole thing here, we pulled out and called that du? Right? So we're using kind of the same notation. If you saw differential notation in Calc 1, that's what you did. All right? I got a question mark over the equals because we just did something funky here. What did we do? We're saying let's take the antiderivative of this thing with respect to u. Forget x. Forget x. So we've just dropped this and said du. So we're going to take the antiderivative with respect to u. Okay? Well, suppose we did that. Let's just, for a minute, let's suppose. What would happen? Well, this is the derivative of f of u with respect to u, and then this is the antiderivative of that. So what does it give us? It gives us back f of u plus some constant. So this is the whole family of expressions that if I took the derivative, no matter what c is, if I took the derivative of this, I'd get back df du. Now, what if you stuck back in for u g of x? If you substituted that back in, what would you get? Well, you get f of g of x. And I should put plus some constant. So look what we've done. We've shown that, actually we've shown the substitution rule right in here. We've gotten rid of this equals mark right there. Sure enough, those are equal with the understanding that once you compute this antiderivative, this integral with respect to u, then you will go back in the end and substitute in what u is with respect to x. So if you do a substitution with respect to u, then what you've got to do is, well, let me show you the game. Let me show you the game. If you're given a function of x and you're trying to find the antiderivative, this is the substitution rule. What we've found is that we want to look at that function of x and find some expression g of x. And it is a craft, not quite an art. I have another meaning for art, but it's a craft, meaning that you have to be clever about it, you have to be experienced about it. Sometimes if you can pick 100 different things for g of x and it would go woefully wrong, but if you just pick the right thing for g of x, often something wonderful and marvelous happens. So suppose we pick just the right expression g of x, and everywhere we're able to go into this function and divide it into two parts. We can find parts of the function where we can substitute in, everywhere we see a g of x or collect together g of x, we can substitute in things and call them u. And then the leftover stuff with respect to x is actually the derivative of u, the derivative of g of x with respect to x. So we break it into a product of two parts. Then this part right here we replace with du. So now we're actually looking at a new function of u, and we're trying to find the antiderivative with respect to u. And then once we find that answer, we'll substitute back in u and for g of x and for u, and we will have the answer to the original integral. That's what the substitution method is. Oh my goodness, this is 9 minutes, but I've cut it down a lot. I'm going to stop there. You see the example I'm going to try on the next video, okay? So that's substitution method explained. Beautiful stuff, and I hope that helped.